Welcome to This Explainer. Today, we're doing a really professional, incredibly detailed analysis of an absolute masterclass presentation on AI factory infrastructure. When we talk about AI, it's always GPUs this and LLMs that. But the real unsung hero, the actual network infrastructure, we're going to completely decode how the biggest tech infrastructures on the planet actually talk to each other. So let's dive right into the blueprint. Okay, to really understand gigascale AI, we have to fundamentally flip how we think about computing. We've got to stop looking at individual servers. Honestly, even looking at individual racks of hardware is too small. Here's the new paradigm. The entire data center is the computer. That's the computer. And the piece that actually defines what it can do, how fast it thinks, and how efficient it is, that's the network. Think of AI infrastructure like a massive 5-layer cake. Right at the top, you've got your applications and your models, but for our analysis today, we're cutting those top 2 layers off. We are focusing purely on the foundational bedrock, the bottom 3 layers: energy, chips, and infrastructure. Because frankly, without those bottom layers operating in absolute perfect harmony, all that fancy stuff at the top literally just collapses. So here is exactly how we're going to break this down. We'll start with the AI factory's base infrastructure, then move into zero jitter and the 4 networks. After that, we'll look at Spectrum-X and long-distance transmission, followed by co-packaged optics and storage. And finally, we'll wrap up with digital twins and topology. Section 1. AI factory's base infrastructure. The fundamental challenge here is syncing hundreds of thousands of GPUs so perfectly that they act like a single unified brain. To pull that off, engineers enforce something called the rule of zero, as in zero jitter. Think about it. You're running a massive workload across 100,000 GPUs. If just one single GPU gets its data a microsecond late, the whole system stalls. You literally have 99,999 incredibly expensive GPUs just sitting there, completely idle, waiting for that one latecomer. Every microsecond of jitter is just straight up wasted energy. And this is a massive departure from traditional networking. Standard off-the-shelf Ethernet was built for single-server workloads. You fetch a web page, there's a tiny bit of jitter, whatever. Human users are never going to notice. But an AI factory? That's a highly distributed computing environment. Jitter isn't just a minor annoyance. It is absolutely fatal to performance. So we have to intentionally design a specific AI Ethernet where zero jitter is non-negotiable.
Section 2. Zero jitter and 4 networks.
Now, to actually achieve that zero jitter holy grail at scale, an AI factory's nervous system relies on 4 very distinct networks working together. First up, you have the scale-up network. This is all about syncing local GPUs into a single unit using extreme high-bandwidth connections like NVLink. Next, you have scale-out. This connects hundreds of thousands of GPUs across different racks all over the building. Then, scale-across. This actually links entirely separate remote AI factories together without letting the physical distance kill your performance. And finally, context memory. This is a dedicated network built purely for handling the massive, ever-expanding memory caches you need for AI inference. Section 3, Spectrum-X and long distance. So how do you actually build this? You definitely can't just plug in one magic device and call it a day. It requires a completely co-designed end-to-end architecture. Spectrum-X pulls this off in 3 really brilliant steps. Step 1, the switch handles global load balancing. It finds the absolute best path for data without any artificial constraints. Step 2, the SuperNIC. This takes that data and sequences it directly into the GPU memory. Zero buffer copy, no extra overhead. And step 3, the sonic operating system. This is constantly monitoring telemetry across the entire network, adjusting injection rates in real time so data only flows when the system knows for sure there won't be a traffic jam. Let's put that into perspective against traditional setups. Old-school, long-distance switches rely on these massive deep buffers. When there's congestion, they just hold on to the data, trying not to drop packets. But holding data, that multiplies your latency by 2 or 3 times. No way you can do that in AI. Instead, we use dynamic control technologies, like Skeleclaw. This actively adapts its algorithms based on the physical distance. Short distance, it gets super aggressive. Long distance, it intelligently throttles the injection rate. You end up with near 100% bandwidth efficiency across huge distances, totally bypassing the crippling latency of those old deep buffers. Section 4, co-packaged optics and storage. As these factories get bigger and bigger, the physical hardware limitations become just as crazy as the software routing. To cover these massive distances inside a factory, you need optics, lasers. Traditional data centers use mountains of copper wire, and traditional pluggable optics use a ton of power and have way too many individual parts. The game changer here is co-packaged optics, or CPO. They literally bundle the optical engine directly alongside the switch silicon in the exact same package. By doing that, they've achieved a staggering 4 times reduction in the number of lasers required. And the return on investment on that physical co-design is just wild. Because these co-packaged optics are completely sealed, ruggedized, and liquid-cooled, they need zero human touch, no maintenance. The result? You get a 5x increase in AI factory uptime compared to the old pluggable models. Just a massive, massive leap in reliability. That same philosophy of co-design extends right into how we handle storage, especially for that context memory network we talked about earlier. Enter the BlueField STX. This is a specialized processor completely co-designed with the GPUs and the storage hardware. Instead of burning up your incredibly expensive GPU compute to manage massive inference caches, BlueField just offloads all of it. The numbers speak for themselves, a 5x increase in token throughput, perfectly matched by a 5x increase in energy efficiency. Plus, you get a solid 1.5x performance boost over traditional Ethernet setups.
Section 5, Digital Twins and Topology.
Okay, so think about this. How on earth do engineers actually test and manage a multi-billion-dollar deployment without accidentally breaking everything? You simply cannot afford to have 100,000 GPUs sitting offline while you debug some network config. The solution? A digital twin. Using tools like the DSX simulator, engineers create a complete, pixel-perfect virtual replica of the entire factory. Every single switch, cable, and GPU is simulated. What used to take months of physical racking and debugging now takes just weeks of validation in the digital twin. And rolling out a massive software update, that drops from months of scary testing to mere days. You validate it digitally, you click a button, and you deploy a literally flawless configuration to the real factory. Now, a flawless software config still needs a flawless physical topology, the actual wiring. In the past, GPUs connected to single-rail networks, which essentially just created these giant congestion bottlenecks. The massive evolution here is moving to multi-rail and multi-plane topology. Instead of trying to shove all your data through one giant pipe, a massive 800 gigabit port is split up into multiple hardware-managed lanes or planes. The load balancing happens instantly right in the hardware logic, completely bypassing slow software routing. And when you look at why topology matters so much, the stakes are just incredibly high. If you're on a traditional single-tier network and one switch dies, boom, you suffer a 100% bandwidth loss for those specific connected GPUs. But if you use a multi-plane architecture, you can scale out a massive 2-tier network that supports up to 128,000 GPUs. If a switch completely dies in that setup, you only lose about 6% of your bandwidth. The entire system barely even flinches. Finally, to keep a beast of this size running, the network actually has to monitor itself. Using an AIOps framework, the system is continuously pulling in telemetry data from absolutely every component across the entire data center. It's using AI to run deep, real-time analysis on itself. Picture this. You're managing 10 massive gigawatt-scale AI factories. Performance drops by a fraction of a percent. AIOps can instantly dig through the mountains of data and diagnose the root cause down to one single faulty physical cable out of millions. It is literally breathtaking engineering. So we started this explainer by saying the data center is the computer, and the network defines its capability. From zero-jitter routing to liquid-cooled optics, every single piece has to be co-designed to fuel this AI revolution. So I'll leave you with this question. As we firmly enter the era of gigascale AI, is your network just a bottleneck, or have you engineered it to become the computer itself? Thanks for joining me for this analysis, and keep learning.